How's quiz 1?
Excuse me, can dissolved hydrogen carbonate actually react against it?
What is that?
Can dissolved H2CO3 actually react against it?
Absolutely. How do you think it'd get categorized as a Bronsted acid?
Okay, well, I think I got
Has to react with water to be categorized as a Bronsted acid. I'll soon post the key. I expect by no later than tomorrow. And you will, of course, get these quizzes back after they've been graded and the grades recorded. And as I said, as soon as I can, I'm going to develop bonus quiz 1. But we have no time rush on any of the bonus quizzes. More on that when I make such available. Now, last time we arrived at a very important relationship regarding Bronsted-Lowry acid-base chemistry. We discovered that for a Bronsted-Lowry acid, whose ability to ionize is subject to equilibrium control, which is a rather elaborate way to refer to a weak acid, an acid for which in our table you see a Ka value tabulated, and its conjugate base. The value of Ka for that acid and the value of Kb for its conjugate base multiplied times each other is equal to Kw. Upshot, if we need Kb for any Bronsted base, and we've got a table of Ka values, like our table, we don't need a list of Kb values. So you can calculate them all. If instead we listed the Kb values, we would need a list of Ka values. But it's more common practice to list the Ka values. So that's what we have listed in our table. Illustration. Look at the table. How do we get Kb for bicarbine? Well, to use this relationship, the first thing you have to realize is what the heck is the conjugate acid of bicarbine? What is it? It's quote-unquote H2CO3. And if my memory's right, that's 4.2 times 10 to the minus 7. So tell me, if I take 1.0 times 10 to the minus 14 and divide it by 4 times 10 to the minus 7, we'll simplify the arithmetic. Instead of 4.2, we'll use 4. 1.0 times 10 to the minus 14 divided by 4 times 10 to the minus 7. What do we get? I don't want any pocket calculators for this. Well, let's take 1.0 times 10 to the minus 14 and rewrite it as 10 times 10 to the minus 15. I do this because if I divide 10 by 4, you can all tell me the answer is, what is it? 2.5. But I've also discovered that if I choose to divide 1.0 by 4, a lot of students short circuit. That's terrible. That's because you've been mistaught. It's not your fault. But we're going to try to deprogram you from that mistaught stuff and get you to be able to do arithmetic, simple arithmetic, with the best computer you got, this thing. I don't know if as yet I've mentioned that our language is 2 parts, alphanumeric. Have I told you that? Numbers and letters. And if you have to do the numbers part with this push button gadget, you can't speak half the language. And if you can't speak that half the language in science class, you got a big problem. Or math class. We don't want that. So whenever you have an arithmetic problem with which to wrestle, always think about it first with this computer. And get the cobwebs dusted off. Always use this one before you start using this one. All right? So the gee whiz Ka of bicarb ion is how much? 2.5 times 10 to the... How about that? Now I know if I divide by 4.2, I expect to get a somewhat smaller value than 2.5. In fact, I get 2.4. The 2 sig figs, the true Kb for bicarb is 2.4 times 10 to the minus 8. Now, of course, in our acid-base table, you see the Ka value listed for bicarb. But if you didn't have the Ka value listed for bicarb, but instead had a list of Kb values, the Kb for which base would you use to calculate Ka for bicarb? Carbonate ion, because that's the conjugate base of bicarb, when bicarb is viewed as an acid. Now then, let's start to lay foundation for dealing with the analysis of acid-base systems quantitatively. Consider sodium bicarb solution. It doesn't matter that it's 10th molar. Maybe we could consider half molar, 1 molar. Based on what we've just considered, is sodium bicarb solution acidic, basic, or neutral? And if it's acidic, is it strongly acidic or weakly acidic? If it's basic, is it strongly basic or weakly basic? 5 possibilities. Strongly acidic, weakly acidic, neutral, strongly basic, weakly basic, or mildly basic. So those are 5 choices. How many vote neutral? All right. That means it's acidic or basic. How many vote acidic? I'm looking around. My magic camera is running. If you don't vote, recognize that exam 1 is next week, Thursday. Those who don't vote, I'm taking off 2,000 points before you even see the exam. Woohoo! How many vote the solution is basic? Well, we're batting about 50%. Half-half. All right, for those who voted acidic. Strongly acidic? Mildly acidic. For those who voted basic. Strongly basic? Mildly basic. The mildly basics are right. Of course, the important question is, why are they right? Now we want to realize what these K values mean. Ka for bicarb, it's in the table, take a look. 4.8 times 10 to the minus 11. So I told you if you do this enough, you'll see the table in your sleep. Don't have to worry about that. And Kb for bicarb we have just reckoned with. That's 2.4 times 10 to the minus 8. So I'm looking at these two numbers. 4.8 times 10 to the minus 11 measures the ability of bicarb to react with water and make hydronium ion. 2.4 times 10 to the minus 8 measures the ability of bicarb ion to react with water and make hydroxide ion. Which value is bigger? Ka or Kb? Kb. It's bigger by what factor? How much? How many times bigger is Kb bicarb than Ka bicarb? I don't want any pocket calculators. I want the value. What is it? If you know the value, I want you to yop the answer. Have I mentioned as yet yop? How many of you are familiar with what I consider to be a wonderful movie, The Dead Poets Society? Robin Williams. Remember when he was trying to get his students to interact with him? And then what student in the class who was somewhat reserved, didn't want to exert himself, didn't want to express himself. Robin told him to yop. That's an old Gaelic word which means shout loudly and boldly. If you know the answer, I want you to yop it. Ka bicarb divided by Kb bicarb is what? Yop it! 500. Damn it! 2.4 times 10 to the minus 8 divided by 4.2 times 10 to the 4.8 times 10 to the minus 11 is not difficult arithmetic. 2.4 divided by 4.8 is 0.50. Right?
Yes.
And 10 to the minus 8 divided by 10 to the minus 11 is what? It's 10 cubed, or 1,000. So I got to move the decimal point 1 unit, which means I get 500. And that kind of stuff you need to do with this calculator, not this damn push button thing. And then you can speak the numbers part of our language, which is extremely important in science class. So I hope my yupping to you about this has gotten your attention. You need to be able to do this. And I know you've been deprogrammed from this most valuable activity by lousy high school arithmetic classes, math classes. Unless you went to a good high school where they said, he who brings in here a calculator will be thrashed within an inch of the life of his calculator. The calculator is a wonderful tool, but damn it, you need to understand what that calculator is doing. That's why you got to use this one first. All right? So given that Kb is 500 times bigger than Ka for the species bicarbine, we know the solution is basic because the larger Kb tells us that bicarb is stronger, more capable at reacting with water to make hydroxide ion than it is in regard to its ability to react with water and make hydronium ion. That dictates the solution to be basic. Now why mildly or weakly basic rather than strongly basic? Now you got to understand what the magnitude of these K values mean. Do you think it's fair to say that if a solution has a hydroxide ion concentration that's less than 100th molar, I'll pick a number, has a pH less than 12, that's not strongly basic? We'll take that to be mildly or weakly basic. And with a Kb value of 2.4 times 10 to the minus 8, do you think it's possible, even though we haven't done any arithmetic with this yet, but we're going to, do you think it's possible for bicarb to react with water and make a solution that's got a pH of 12 or greater? A hydroxide ion concentration of 1 times 10 to the minus 2 or greater? I'm asking you to think about what this 2.4 times 10 to the minus 8 number means, because we've already looked at K expressions. We already have recognized what Ka is by definition and Kb. Do you think that's possible? Nowhere. No way. Impossible. And if you don't recognize the arithmetic proof which underlies this statement, you will soon. Now let's ask one more question, which lays foundation for something we will be wrestling with in the future regarding bicarb solution. In bicarb solution, what is the principal Bronsted-Lowry acid-base equilibrium reaction? You know how to play the game. You write your PSI, don't you? And in this PSI you see Na plus, who gives a damn, but it's there, and bicarb ion and water, that's it. So you pick out your best acid, which is bicarb ion. You pick out your best base, which is Bicarb ion. How about that? So you now got a system where bicarb ion reacts with bicarb ion. Products will be quote-unquote H2CO3 and carbonate ion. Your task is to calculate pH for this solution. How the hell are you going to do it? Because what does pH reflect? Hydronium ion concentration, or implicitly hydroxide ion concentration. That's what you know from pH, and you don't know anything else from pH. So you've now written the equation for the principal BLAB equilibrium reaction in bicarb solution, and this reaction does not involve hydronium ion or hydroxide ion. So how are you going to calculate pH? Ooh. You'll discover that to calculate pH for this solution, in addition to Ka bicarb and Kb bicarb, you will need to apply the concept of material balance, which we're going to talk about. Oops. In just a moment. And then in a few more lectures down the road, we'll talk about the remaining consideration that's necessary to give us the ability to analyze in detail the composition of any Bronsted-Lowry acid-base aqueous solution system. That remaining consideration is called charge balance. It's a simple concept, charge balance. Charge balance says simply, any system, bulk system which contains charged particles, ions, must be electrically positive, negative, or neutral. Neutral. You think you can go to the laboratory and pick up a bottle that's only got sodium ions in it? You're now in 46L, in assignment 2, I should imagine. You've done some work for sodium ion, right? Flame test. It's the only test we use for sodium ion. A long time ago, when I taught that laboratory course, I had a student coming to me rather distraught. The direction was to do a flame test on sodium ion. And he says, I went to the side shelf and I see sodium chloride and sodium chloride solution and sodium nitrate solution and sodium carbonate and blah blah, but I don't see a bottle that just got sodium ion in it. So I posed to this student the consideration. I said, do you realize that sodium ions are made by sodium atoms losing electrons? One electron per atom makes me a sodium ion. Okay? Now, along with this, as you create the sodium ion, what else are you producing? Na goes to Na plus what? Electron. You got to take away this electron from the Na atom to turn it into Na plus. Well, if the Na plus stuff was stable all by itself in a bulk sample, I could collect these Na pluses as ionized sodium atoms. I could also collect the electrons. I mean, if the Na pluses are stable, then the other part of this reaction must also be stable, electrons. So I have a brilliant idea. This is me talking to the student. You collect the electrons, and now you can do your flame test. I will collect you collect the sodium ions. You collect the sodium ions, so now you can do your flame test. I'm going to collect all the electrons. And I have you repeat this process time and again, so I get big storehouses of electrons. And I'm going to set up a sign. Horvath Electron Store. And I'm going to sell these electrons in bottles. And all people, including myself, can now get this bottle of electrons. You go home. Okay? You go to the socket on the wall. You get out a funnel, you jam the funnel in the socket, you pour in the electrons. And the electrons flow around. And the radio radiates, and the television televates, and all that stuff. And I call up GRU and I say, go to hell, I don't need you anymore. But can't do this, can I? Because these NA pluses are not stable all by themselves. And then the student says, aha, thank you. And he went and took a sample of sodium chloride, which is rich in sodium ions, and did his flame test. More on that when we get to charge balance. But I'm rather fond of that story. But it's important because it underlies the substance of charge balance. All right? Oh. Back to acid-base chemistry. We talked about this. Now Ka water, which by the way is equal to Kb water. I should hope I don't have to explain that. Because the reaction for which the K value corresponds to Ka water is the same as the reaction which corresponds to Kb water. Because this thing makes, by reacting with water, this stuff makes hydronium ion, and this stuff makes hydroxide ion. Remember how Ka is defined? The solute acid reacts with water to make hydronium ion and a conjugate base. Kb. Solute base reacts with water to make hydroxide ion and conjugate acid. Well then, this reaction defines Ka for water as well as Kb for water. But textbooks, I'm sorry to say, often do not recognize how Ka is defined. And so they try to tell me that Ka water and Kw water are the same. And I say, you flunk. Because Ka corresponds to the resulting hydronium ion concentration, molarity, times molarity, conjugate base, divided by the resultant equilibrium molarity of the ionizing solute acid. What's the solute acid in this system? It's water. So I agree. When we write Ks for reactions in water, we leave out solvent water, we leave out solids, but you don't leave out reactant water. That's the reacting acid in this system. And it must be included to calculate Ka or Kb water. So here it is. There's Ka, which of course this is Kw, divided by the molarity of water and pure water, which we've already talked about. The 3 sig figs is 55.5. So there's what we get. That's where now you realize why in our acid-base table you see for Ka water this number. And now you also know that for Kb water it's the same number. All right? Now in our acid-base table, you also see Ka hydronium ion, which happens to be magnitude-wise equivalent to Kb hydroxide ion. How do I get Ka hydronium ion? Well, in this case, let's get Ka hydronium ion from our Kw equals Ka times Kb relationship. Because we have just gotten Kb for the conjugate base of hydronium ion. The conjugate base of hydronium ion is nothing but good old water. So Kw 1.0 times 10 to the minus 14 is equal to Ka hydronium ion multiplied times Kb for the conjugate base of hydronium ion. There it is. And what does this happen to equal? The molar concentration of water, pure water, 55.5. All right? Now let's get at this next consideration, material balance, which is very important. If we are going to succeed from an Bronsted-Lowry acid-base standpoint in analyzing in its entirety the composition of an acid-base system, and in many instances this is very important, Beside Ka and Kb considerations and Kw, you need material balance and, as I have mentioned, charge balance, which we'll look at in the future. So I wrote over here, important, necessary for a complete species inventory of solutions of Bronsted-Lowry acids and bases. Material balance says, for the species in question, as an example, we're going to consider water. You write down how many moles of that stuff you have in the system. And then you also write down how many moles you have of the conjugate acid of that stuff in the system. And how many moles you have of the conjugate base of that stuff in the system. Now sometimes you don't have both, but for water you do. So material balance depends on Bronsted-Lowry acid-base chemistry, because the conjugate acid of the solute and the conjugate base of the solute are produced by H plus gain to make the conjugate acid and H plus loss to make the conjugate base. You know this already. All lies on conjugate theory. And you're understanding what conjugate theory is about. So complete material balance for water in any water solution is a summation of moles of water that you have in there, plus moles hydronium ion, plus moles hydroxide ion. Now then, if I'm dealing with a solution that I know to be acidic, which of these terms do you expect to be able to neglect without causing any error in your calculation?
Hydronium.
If the system is acidic.
I'm sorry.
I thought you'd be sorry.
I meant to say hydroxide.
Good. And if the system is basic, okay? Notice that if a water system is acidic, that guarantees that moles of hydroxide ion is smaller than what value on a per liter basis? Smaller than what value on a per liter basis? 1.0 times 10 to the minus 7. That's pretty damn small. And if the system is basic on a liter basis, you got to have less than 1.0 times 10 to the minus 7 moles of this stuff. Not much. But on a liter basis, when waters are solvent, you know you got a substantial quantity of water. You know, on the order of 55 moles, more or less, if the solution is dilute. Okay? So then, what we refer, or another word we use to refer to these species produced by H plus gain or H plus loss, is viable forms of principal species. What's this word mean, viable? Possible. Those which can exist. Question?
Where did you get the 1.0 times 10 to the negative 7?
Tell me, if a water solution is neutral, how do the hydronium ion and hydroxide ion concentrations compare?
They're equal.
They're equal. And in pure water, that's how much?
Wait, I'm sorry.
In pure water, what is the hydronium ion concentration? In pure water?
1.0 times 10 to the negative 7.
Yeah. It's the same as the hydroxide ion concentration. But if it's acidic, the hydronium ion concentration goes up while the hydroxide ion concentration comes down, and vice versa for basic.
What if it's only like slightly acidic, just a little bit?
And so what? I mean, what are you getting at?
Well, then the if let's say the pH is 6.5, that means the moles of.
Are you asking, is it sometimes the case where we have to consider both mole quantities?
Yeah.
Yeah, but it's not a problem. Because once you know this, you can always calculate this and vice versa.
Okay.
That's what KW allows you to do, okay? So, there's no problem if we need both of these. We can get them. And we'll see cases where you do. All right, now let's ask one more question before we do some work with this material balance consideration. Viable forms are those species produced by H plus gain or H plus loss. Well, let's imagine that hydronium ion there's a Lewis picture of hydronium ion, oxygen central atom, trigonal pyramidal. And clearly with this non-bonding pair, we can, at least from a theoretical standpoint, imagine this species to be capable of collecting yet another H+. Because we realize that's how hydronium ion is formed. H+ with its empty valence orbital interacts with a non-bonding pair on the central oxygen atom for the water molecule, make hydronium ion. Well, here's hydronium ion. Let's imagine that this non-bonding pair interacts with another H+ and makes us this thing. H4O2+. Is that a viable form of water? Clearly it's a form producible by H+ gain and loss, but is it a viable form?
Not in an aqueous solution.
Why not?
Because the strongest acid that can exist in water is its conjugate acid, which is H3O positive.
All right, I'll accept that. And if nothing else, if this did exist in measurable amount or concentration, we'd have to tell you this. How about oxide ion? Here's what you get from water after you doubly deprotonate the water molecule. Can I have a measurable molarity of oxide ion in water solution? No. Why not?
The same principle except with hydronium.
What is that?
It's the same principle except with HO minus. You can't have any.
All right, I'll buy that. And in our acid-base table, do we not recognize oxide ion to be the strongest base listed in our table? Oxide ion reacts with water to what extent?
100%.
100%. You're not going to have any oxide ion floating around. All right, so these are out. So here's a complete list of viable forms of water in any water solution. Water itself, hydronium ion, hydroxide ion. Now let's put this material balance concept to use. Question 18, on page 1822, I ask you to consider a 1.0 liter volume of a hypothetical acid, formula 8Z, for which I stipulate that the ionization extent of 8Z is 95%. Now, if 8Z was a real acid, we could easily verify this by conductivity measurements, by pH measurements. Okay? We are asking the question, based on this information, if I want to put 8Z in my acid-base table, will it be positioned above hydronium ion and recognized as a strong Bronsted acid, or underneath hydronium ion and recognized as a weak Bronsted acid? We want to put 8Z in our acid-base table. So from a Ka standpoint, we're asking if this acid HX has got a Ka value that's bigger or smaller than 55.5, because we now know that Ka hydronium ion is 55.5. But we're not going to do this by Ka calculation, which you will realize as we talk through this question, you could. We're going to do this by material balance considerations. And I purposely selected a volume of 1.0 liters, because in a 1.0 liter system, as we've already noted, mole amounts and molar concentrations are numerically equivalent, because I want you to focus on the chemistry and not be puzzled by arithmetic. And now comes the material balance fun. Bronsted bases are noted for their ability to steal H plus protons, right? That's what Bronsted bases do. They steal, they capture H plus protons. Ha ha! But bad kids, bad kids have a habit of stealing candy bars. So we are going to imagine this scenario. I'm a bad kid, and so are you. Before us stands a candy bar warehouse of our favorite candy bar. Okay? If you and I are equally capable at stealing candy bars, and we break into the warehouse, and we're in there for the same amount of time, when we leave the warehouse, what will be the ratio of candy bars you have to those which I have? If there was one of you, one of me, we're in the warehouse the same amount of time, and we're equally capable at stealing candy bars. What will be the ratio of candy bars you have to those which I have when we leave the candy bar warehouse?
1 to 1.
That wasn't hard, was it? Now let's change the situation. This time when we break into the warehouse, there's 55 of you. Does that number sound familiar? And one of me. We're still equally capable at stealing candy bars. But this time there's 55 of you and only one of me. We're in there for the same amount of time. What now will be the ratio of candy bars you have to those which I have when we leave the warehouse?
55 to 1.
Bingo! Now let's change the game again. There's still 55 of you and still just one of me. But this time you're even better. You're better at stealing candy bars than I am. So we're in there the same amount of time. 55 of you, one of me, and you're better at stealing candy bars. When we now leave the candy bar warehouse, how will the ratio of the candy bars you have to the candy bars I have compared to 55 to 1? Be bigger than 55 to 1. Maybe 80 to 1, maybe 100 to 1. We don't know how much better you are. We just stipulated that you're better. Now one more variation in this theme. 55 of you, one of me, we're going to be in the warehouse the same amount of time, but now I'm better. Ha ha ha. Now when we leave the warehouse, how will the ratio of candy bars you have to those which I have compared to 55 to 1? Smaller. See, that's not hard. And that's material balance. Now let's see how this material balance consideration applies to protons being stolen by bases. .0 liters. All right? Let's imagine that VZ minus equals V, HZ equals V, H2O equals V, H3O plus. Because I don't want difference in volumes following up this question. When I prepare this solution, before I talk about the chemistry that occurs when the solution is prepared, when I prepare this solution, given that I've made 1.0 liters, and it's 1.0 molar, we recognize that if it's all water, it's 55.5 moles, right? But now I got a mole of HZ in there. So based on these volume equivalents, which I've stipulated, how many moles of water will I have after I prepare this solution? 54.5. Right? Because of all this liter volume is no longer pure water. It's got a mole of this HZ stuff in there as well. Well, let's simplify that even more. Let's imagine that the volume of a mole of HZ is a little bit bigger than that of a mole of water. So I can get rid of the decimal parts. So we're making a mix, which winds up having a total volume of 1 liter. 54 moles of water, 1 mole HZ. Now let's pay attention to the chemistry that occurs, because we have learned that if you're going to do anything with a chemical system, you have to know the chemistry which occurs when the system is prepared. Well, we'll do this. We recognize that this reaction occurs, and if the label on the bottle is 1.0 molar HZ, then the extent of this reaction is 95%. That's what I have stipulated. And after this reaction is proceeded to this extent, then what condition sets in? Good. We now want to pay attention to material balance for this system at equilibrium. And reconsider material balance from the standpoint of total moles. Let's write this down. Now consider MB based on total moles each BL base. Quick. What are the two BL bases of consequence in this system?
H2O and Z minus.
Water and
H8.
water and Z minus. Bingo. What are we going to write down for total moles water? Based on what we said, 54. Now think about this before you answer. What are you going to write down for total moles Z minus? Don't forget this business. Because what are the forms of Z minus in this system? See, total moles water equals moles water plus moles what else? For material balance water. Moles water, moles what else? What? Hydronium ion. Hydroxide ion, forget that. It's an acidic system. And total moles Z minus is equal to 1. We'll write it as 1.0. Equals moles free Z minus plus moles HZ. Okay? Now let's go back to this. This went 95%. So after this reaction has proceeded, what will be moles of this, which will be the same as molar concentration of this? What is it? 0.95. This will be 0.95. This will be how much? 0.05. And this will be ball game what? 53. All right? So we have a ratio. Thus, ratio of bases based on MB equals 54 to 1. Right? 54 to 1. Remember this candy bar stealing business? Now, after candy bars were swiped, which in this case are protons, how many moles of hydronium ion do we have? 0.95. How many moles of HZ do we have? Because when water grabs this candy bar, it becomes hydronium ion. And when Z minus grabs its candy bar, it becomes HZ. Ratio of bases. Ratio of acids is 0.95 to 0.05. Quick like a bunny, what's this equal? 19. to 1. Who's the stronger base? Do we have to go back to the candy bar warehouse? If there's 55 of you and 1 of me and we're equally capable at stealing candy bars, when we leave the warehouse the ratio is 55 to 1. But if I'm better than you when we leave the warehouse, how does the ratio compare to 55 to 1? It is what? Smaller. And this time, which of these bases am I? Z minus or water? Only one of me. I'm Z minus. And look what happened after we got done stealing candy bars. The resulting ratio of acids, 8Z, after Z minus stole its candy bars, to water, after it stole its candy bars, is 19 to 1. Who's the better base? I'm Z minus. I go into this warehouse. You're water. We leave the warehouse. The ratio is much smaller than 55 to 1, or 54 to 1 in this case. It's 19 to 1. Who's the better base? Z minus is the better base. Which means by conjugate theory, if Z minus is a stronger base than water, how does the acid strength of HZ compare to that of hydronium ion? It's got to be weaker. Absolutely. We'll pick it up from this point next time.